for my theme song.
Math is so much fun for everyone. Math, yeah, math. Numbers, symbols, shapes, and signs. We use math all the time, yeah, math. Numbers, I see numbers everywhere I look. Price tags, speed limits, calendars, and books.
I love math.
What kind of math, though?
Calculus.
Oh, no.
Hello class, I'm Maggie Weber, and today we're going to learn about evaluating limits. Dominic should have already told you guys what a limit is, so today we're going to talk about how we evaluate them and how we use them to solve problems. Direct substitution is the first method of solving a limit. It's the easiest, and it's the one that you're going to want to look for, okay? This is an example of a really, really basic structure. It's going to be the limit as x approaches c of x is c. Get this down. It will help you in the long run, very much so. Now it's time to show you an example of how you use direct substitution in a real problem. Okay, here's a problem right here. The limit as x approaches 2 of 4x squared plus 3. How are we going to solve this? Direct substitution. Basically, all you do is you plug in the 2 where the x is, like in our standard equation, and you will end up getting 19, because 2 squared is 4. 4 times 4 is 16 plus 3 equals 19. So limit as x approaches 2 equals 19. Can't get much simpler than that. But what do you do if you can't use direct substitution? Here's an example of another problem. The limit as x approaches negative 3 of x squared plus x minus 6 all over x plus 3. Now, what do we think of to do first? Easy. Let's just direct substitute, right? Wrong. What do you get when you plug in negative 3 to this problem? Let's do some math. This is what you'll get. And if you simplify this all down, you get 0 over 0. Okay. Never write that on an AP calculus exam. They will take points off, and they will do it cold-heartedly. But that's besides the point. That's an indeterminate form. Indeterminate forms are no good. 0 over 0 is not an answer. Again, never write that on your exam. We have to use a different method. Wow. My board is clean. I have to write the title. Factoring. When direct substitution does you wrong, you factor. Now, let's take that problem that we just got an indeterminate form on and see if we can figure it out and get the answer to that limit. Factor. We can factor this, what's it called? Numerator. We can factor the numerator here, and when you factor it, you get x plus 3 and x minus 2 all over x plus 3. Are you seeing what I'm seeing? Because I'm seeing some simplification getting ready to be made. Boom, boom. Yes. Look at that. Goodbye to this denominator. And now we're left with limit as x approaches negative 3 of x minus 2. Plug it in. Use direct substitution right there, and we get limit as x approaches negative 3 equals negative 5. Just like that, easy peasy. Now imagine this. You're given a problem that you can't direct substitute with, and you can't factor it out, you can't simplify it. What can you do? You can rationalize. here's an example. So limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. Now, step 1. Can we direct substitute?
Oh.
No, you can't, because there's only an x on the bottom. You're going to get an indeterminate form. No good. Can we factor? I don't see anything. This is an excellent math student. Do you see any opportunity of us factoring that out?
No.
No, there's nothing you can do. So what are we going to do? Read that right there.
Rationalize.
We're going to rationalize this function. I'm going to show you how. We're going to use the numerator to rationalize. Now, you probably remember this from pre-calculus or whatever math you took. To rationalize this equation, we multiply it by the conjugate of the numerator. We multiply both of these by the conjugate of the numerator. So, in this case, it would be the square root of x plus 1 over the same thing. I think you guys should all know how to find the conjugate form, and how to rationalize a fraction. You guys should know how to do that, I think. But basically, all you have to do is change the sign connecting the two terms. So yeah, that's basically all it is. So once you multiply both the top and the bottom by this, you're going to be left with this. Yay! Something we can easily simplify. Let's get some simplifying done. All right, so you can cross out these ones because it's going to be x plus 1 minus 1, and that's just going to be 0. So cross those out. So you're going to be left with x over x times square root of x plus 1. These x's are going to get crossed out. So we're going to be left with a pretty simple equation. You're going to be left with a simple equation of 1 over square root of x plus 1. Is it minus 1? This is the simple equation you're going to be left with. Don't forget to carry your limit symbol. Always put this. Every time you rewrite your equation, carry this little guy. It's a big deal. I got taken off a lot of points on many tests, Mr. Rivera, because I didn't carry that. So do that. Okay. Now we can do direct substitution. Plug in the 0. You're going to get 1/2. The limit as x approaches 0 is going to equal 1/2, and x is not going to equal 0. Ooh. The denominator was only an x, and there will be no zeros as denominators. Next and last section of this section, the squeeze theorem. Now, it's kind of complicated, and these words might not make sense, but I'm going to try to explain it in a way that makes sense later. The squeeze theorem states, if there exists h of x less than or equal to f of x that is less than or equal to g of x on an open interval containing c, and if the limit as x approaches c of h of x equals L, and that equals limit as x approaches c of g of x, then limit as x approaches c of f of x exists and is equal to L. That's a lot of words. So basically, in layman's terms, that means that if two functions have the same limit and they're going for the same point, any function trapped in between those two functions is going to get squeezed, and it's going to have the same limit. Because there's a lot of what's the word? There's a lot of moving parts. There's a lot of atmosphere conditions. There's a lot of conditions that have to apply, but basically it's a pretty simple theorem, but it's a very specific situation. Here's an example of where the squeeze theorem can apply. This is a problem you might be given. Determine limit as x approaches 2 of f of x. That's your problem. You're given g of x and h of x, and you're given the condition that there exists an f of x where g of x is less than or equal to f of x that is less than or equal to an h of x. So those are the conditions you need to apply the squeeze theorem. The first step to doing this is we'll solve the limit for g of x, whereas x approaches 2, and the same for h of x, because they need to be the same limit for the squeeze theorem to apply. So let's do that. Boom. These two no chance for that nasty indeterminate form. So we are simply doing direct substitution. Woo! Yay. Come on. Okay, yeah. Just plug in the 2 where the x is and solve for our limit. And hooray! Yay.
Woo! Yay!
The limit of g of x as x approaches 2 equals -1. And the limit of h of x as x approaches 2 also equals -1. So what can we derive from this? That was awesome. What can we pull from this? So the question, what was the original question we're all asking? Find the limit of f of x as x approaches 2. Right? And so far we don't have that answer. But we do have the squeeze theorem. This function was between the 2. So it was squeezed, and we can conclude that. Let's use calculus words here. Because g of x less than or equal to f of x less than or equal to h of x, the squeeze theorem applies, and the limit as x approaches 2 of f of x equals -1. Tied it up in a pretty little bow, and you have your answer. So that's how you apply the squeeze theorem to some calculus problems. I'm going to show you guys a picture now. All right, here's a picture.
Do I sound like that when I teach? All right, here's a picture.
This is a beautifully drawn picture that should give you a great visual representation of what the squeeze theorem states. So you can see here that f of x is betwixt the two equations, and you can see they are approaching c. If you go back to our original description of the squeeze theorem, limit as x approaches c is like the basic whatever. F of x is squeezed right here, and limit of f of x must be c, because it's that for those two. So that's the squeeze theorem, and now you know. All right, that is 1.3 explained. That should be everything you need to know. Don't forget to carry that limit. Don't forget your squeeze theorem. It's gonna be great. You guys got this. Calculus is easy. That's it.